Hi everyone. Some of you had asked me to explain this question 2 from tutorial 7, so which I thought I'll make a video on it. So if you look at the question 2, it essentially discusses about zero IF architecture and heterodyne architectures. Okay, so I'll briefly first discuss what are the challenges in zero IF and heterodyne, and then we'll discuss the problem again. A zero IF receiver is one in which the signal you receive from an antenna, after it goes through the band, of course it goes through a band pass filter and an LNA, a low noise amplifier, and then a mixer. I mean, this is the down conversion process. Now we discussed in case of an RF amplifier, the problem is the presence of strong interferers because of there are adjacent interferers, which is a big problem in RF systems. Now these interferers, because of these interferers, they have to be sufficiently filtered out by the band pass filter, low noise amplifier, or subsequent circuits after that. So that's the reason why we said we need a big band pass filter at the beginning. So normally these band pass filters turn out to be passive filters, because active filters, building active, for example, a low noise amplifier also behaves like a band pass filter come amplifier. But the problem is that you need those blocks to have very high linearity. So the linearity of this band pass filter is a very important specification, which is why, of course, it might if you do a linear analysis for a narrow range, it might give you, for small signals, it might give you good filtering. But when you apply a large signal, it might start saturating and it might lose its ability to filter. Okay, so we need filters with very high linearity. And more importantly, other important factor is that, and we said that is one spec, and low noise amplifiers linearity spec also will be relaxed. If I put a band pass filter before, the signals that are going to come to the LNA will also be smaller. The interferer signal levels will be smaller. After the band pass filter, the interferer level will be reduced from here to here. Okay, then LNA will further increase this signal level and suppress this signal level, and so on. Eventually when it goes to the next block. So, and also I discussed this very interesting point, that for it's a general rule of thumb. If I filter 1 dB, for every 1 dB of filtering that a preceding stage has, the stage following that can have 1 dB relaxed linearity spec. Okay, because your interference levels are going to be smaller, your linearity spec will also be relaxed. IIP3 spec will also be normally relaxed for the stages that come after sufficient filtering. Okay, because filtering automatically reduces the the interferer levels, so therefore linearity can also be relaxed. Okay, so when I say ideally linear amplifier should have infinite IIP3 1 dB compression points, but that's not practical. So to have some reasonably good linearities, then we need to have filtering before that. There is other important problem, that if your interferer, let's say, is very close to the main signal, then you need a very narrow band pass filter to filter out the interferer. Okay, now let's say we go for a passive band pass filter. A passive band pass filter will relatively be better than an active circuit. Okay, its linearity will be slightly better. But now the problem is you need to have a very high Q for the passive band pass filter. And a high Q, because you are going to offer this filtering, this filter is centered around the carrier frequency. Okay, it's centered around the carrier frequency. A high Q, a very good rejection. So when I say rejection, it is the peak value from here to say some frequency offset here. This value in decibels, if I find the value here and subtract it from this in decibels, it's what we call as rejection. And we discussed in one of the previous lectures that this rejection is simply inversely proportional to Q. I'm using the word rejection. You should be careful there. If you look at the general transfer function, we wrote it like this for a second order system. I just took a second order system to explain what is that. So essentially we had a system of this type, S by omega naught square plus S by omega naught Q plus 1, this multiplied by H of omega naught. This is your gain at maximum gain at omega naught, and this is the second order filter transfer function, the band pass filter transfer function. We said around the resonant frequency omega naught, this system can be modeled as a low pass filter with a cutoff given by omega naught by 2Q. For large values of Q, we said that we can make this approximation. You can model this as a low pass filter centered around omega naught with a cutoff frequency of omega naught by 2Q. So I can model this as 1 plus s by omega p, where omega p is omega naught by 2q. So for frequencies greater than much greater than delta omega much greater than omega naught by 2q or omega p, okay, I'll try to find the rejection at that point. The transfer function of the filter is simply going to be 1 by, I'm taking the magnitude of it, so if I take mod of this, I'll ignore 1 because we have moved away from omega p. It will be simply omega p upon omega. Omega p is nothing but omega naught by 2q into omega, into delta omega, sorry, it's delta omega. So I have to write j delta omega here. I've already done this derivation, so I'm just, it's not very confusing. Hope it's not confusing. So this is the value that you will get here. Okay, so here I've assumed the DC value is 0 dB. If I take modulus of this and take 20 log of this, so 0 minus this quantity, 20 log of this will be the attenuation. Okay, these are just the words. If I give rejection can be positive, if you take plus or rejection is simply 20 log of 2q, I just have to take inverse of this divided by omega naught into delta omega. That's the rejection. Okay, it tells you. So for example, if this is your peak value, by how much the value has reduced from the peak. So if this is 0 dB, this is going to be 20 log of this value. Okay, rejection can be written as 0 minus this peak value minus this value. Okay, so that will be, I can write it in this way. Okay, now if you look at this, the rejection depends upon q. If you want a large rejection, you need to have a large q and you should be away from it. Now I'll fix the frequency offset. Let's say the frequency offset is fixed because that's where your interferer is occurring. Omega naught is your frequency, plus delta omega, you have a huge interferer and you need to meet a certain rejection spec. You need to reject it by a certain amount. Then from this equation there are only two parameters to play around with, 2q by omega naught. Okay, 20 log, of course there is log as well, but I'll just take these two parameters. Now if I fix the carrier frequency, then I'll need to have very high q. If for example my carrier frequency is very high, I mean the RF carrier frequency will be of the order of few gigahertz. That's a pretty high frequency. Therefore the q required will also be pretty huge to get reasonable rejection values. Okay, even sometimes to get rejection of 60-70 dB, you may have to run q in the order of several thousands, and that's practically impossible in RF circuits. Then how do we solve this problem? One interesting way, one very simple way to solve this problem is what we call the heterodyne architecture. So what we do is first we introduce a bandpass filter with a certain q. See, understand this, eventually we need to suppress out the interference as the signal progresses through the RF chain. So let me just redraw the receive chain again. So from your antenna you will have a bandpass filter. This is just to filter out the interferers. Then LNA, here LNA is going to see large interferers, so you have to filter it out. After that mixer is going to see some interferers, that also needs some filtering. Then after the mixer there will be a baseband filter and some gain circuit, a variable gain amplifier circuit as well. They both have to give you high gains. So whenever you have a high gain block, you should always ensure that the input signal should be of smaller value. Okay, meaning your linearity requirement should be tighter. Okay, so linearity is a challenge at that point, so you'll have to ensure that. Now this problem is that the bandpass filter now has to be very linear because your signal is as it is coming to low frequencies, and again you will need very strong cutoff, so your bandpass filter has to be very linear. So to solve this problem, what they do is they go for the concept of heterodyning. So first step, you take your frequency omega naught, and let's say there is a strong interferer here, delta omega away from it. Instead of down converting directly, you down convert it in steps. So first you down convert it to a different frequency called IF frequency. So now both of them are translated. Of course you give some amount of filtering there. You filter the interferer by certain amount. Okay, and then so you will have a bandpass filter which will filter out by with a reasonable Q. You will get some rejection. Then it goes through a low noise amplifier. Okay, LNA, and a mixer. So the mixer will now down convert it to a different frequency called the IF frequency. Then you have to design another filter centered around the IF frequency, omega IF. You choose your local, this is called the local oscillator frequency, yellow frequency or local oscillator frequency. And this is your RF frequency. The input signal frequency is your RF frequency. I'll call it FRF and this as FLO. Okay. So you have to down convert it to a lower frequency FIF. It's called the intermediate frequency FIF. This will be smaller than FRF. Obviously, it will be smaller than FRF. So you will first do a two-step down conversion. First you will down convert it to FIF. Okay. And then in the next step you will do one more down conversion. So the output of this will be fed to another mixer with FIF as your carrier frequency. This will down convert to DC and you will have a baseband filter. Now if you see, there are three stages of filtering here. Filter at this point, there is an IF filter. Of course, we can also insert an amplifier in between here. Okay. And there is one more filter, the baseband filter, which will again go to an ADC or a band pass and another baseband filter, a baseband amplifier. I'll call it BBA or a baseband amplifier. And eventually it will go to an ADC. Now if you see, I get three stages for filtering. One is the first band pass filter, the second IF filter, and the third baseband filter. So you will have three stages of filtering. Now let's say I tell you the rejection necessary is 90 dB for the interferer. Then what can I do? First I'll have 30 dB of rejection at the band pass filter. I'll give 30 dB of rejection for this guy and 30 dB for this filter. So I have split the rejections for all the three filters. Now we know that it's difficult to get high rejection at the higher frequencies. But once you convert it to a lower frequency, the intermediate frequency, it's easier to get a higher Q. I mean, it's easier to have filtering because we just saw rejection was inversely proportional to the omega naught. So as you lower omega naught, rejection will further increase. For the same Q, you can have higher rejection. So I might as well split this as just 10 dB here and give 20 dB to this, 50 dB at the IF frequency. Or I can give 40 dB at IF and 40 dB at lower frequency. I can split the filtering at two different stages. So now if you see, initially for a single 0IF conversion, the necessary filtering was, if let's say if I take a 0IF structure, I'll have to give totally say 90 dB, then 45 dB has to come from here and 45 dB has to come from the baseband filter. The main problem is 45 dB at the higher, the first baseband filter. So this is one crude example. Actually, I mean, you might also question what happens in the linearity requirements. Yes, linearity requirements for the LNA increases. Okay. But I'm not going to give all the gain in the LNA itself. I'll slowly keep increasing the gain slowly, because you know that, you can, by reducing the gain, you can improve the linearity requirements. In case of super heterodyne receivers, there are more stages. So therefore, I can add more gain through the path. Okay, I can split the gain also. So I get all this freedom and go for super heterodyne architectures. Okay. So this way, if you see the rejection required for the first filter, I'll come back to this point. I told you we can only go for some 10 dB. So the Q becomes pretty reasonable at this point. Okay. So that's one of the main advantages of going for heterodyne architectures. So I'll go back to this problem. Okay. Again, if you attended the lecture, I told you heterodyne doesn't come for free. It has its own problems, but I'll just discuss that later. First, I'll go back to this problem. This question is just to show what was the motivation behind heterodyne. Okay. Then we will see there are many problems in heterodyne, not just, of course, it gives you one advantage of splitting the gain among many stages and all that, but it comes with a host of new problems. And that's why 0IF is more popular today. Okay. We have a 0IF architecture is a pretty popular architecture today. In spite of its few limitations, we have more or less dealt with most of its issues. So first, I'll look at this question. So what it says is that, it says that you have a signal and two strong interferers fed to a receiver. It's being received by an antenna. And it's given that the interferers are 20 dB higher than the signal. Now the receiver has to amplify your signal level by 20 dB. So whatever level it is, you'll have to amplify it by 20 dB. So your signal should see an amplification, which means your peak gain has to be 20 decibels. The peak gain of your circuit has to be 20 decibels. And the interferers has to be suppressed by 60 dB from their nominal levels. Okay. So this interferers here, the interferers here has to see a rejection of 60 dB. Okay. So I want to increase this guy by 20 dB and suppress this guy by 60 dB. So if you see, that will be possible. So if you see the graph here, so if I assume this is 0 dB, I have to pass it through a filter. If I assume the interferer levels are 0 dB, then the signal level is minus 20 dB. I mean, signal level is, if I assume 0 dBm as the interferer power, then the signal power is minus 20 dBm. You can see that from this graph itself. So now if I give 20 dB of gain at the signal power, that will become, the signal will become 0 dB. Okay, signal will become 0 dB. Now you should also provide a 60 dB rejection for these two guys. This filter here has to be provided 60 dB. Okay, so let me explain it in a little bit deeper. Here, see, to begin with, your interferers are 20 dB higher than the signal. Okay, so I have to, let's say I pass it through a filter with a peak gain of 20 dB, and if I pass this signal at a frequency offset, say delta omega, which is the interferer location, the rejection has to be, to begin with, it has to be 60 dB, 80 dB, sorry. The rejection has to be 80 dB, the filter rejection. Okay, let me just, if that point is not clear, I will just explain it little. I think it's obvious, but let me just explain it. Let's say we just had two interferers. We are passing it through a filter whose frequency gain, center frequency gain is 0 dB. So center frequency is here, omega naught is center frequency, and the frequency offset away from it, this is delta omega, f1 f2 are here, f1 omega 1 and omega 2 are here. I have used f1 f2, but omega 1 and omega 2 are here. So the peak gain here is 0 decibels. At this frequency, the gain has to reduce by, from 0 dB it has to come to 60 dB. Okay, minus 60 dB. So the rejection here is 60 dB, I can say that. But now what I am saying is that, see, this is what I meant. I have discussed that the interferer should see a 60 dB rejection. But now we know the signal power has to see 20 dB gain. So which means the peak gain should start from, this whole graph has to shift by 20 dB. Okay, so if I shift it by 20 dB, if I design it for minus 60 dB, I mean if I design from the peak, if I design it for minus 60 dB, I will be at minus 40, but we need minus 60 at the interferer level. So we will start with a filter of minus 80 dB. Okay, the interferers should see a 60 dB attenuation. They should see a complete 60 dB attenuation. So that's just a matter of wording. I'll be very clear in the exam. Okay, probably this question wording was not clear. That's why many of you are asking for it, I presume. So what I meant in this question was that, okay, the signal, the signal at omega naught should see a 20 dB gain, and this guy should see a 60 dB rejection. So if they were at 0 dBm, they should become minus 60 dBm. Signal should become, if the signal was initially at minus 20 dBm, now it should become 0 dBm. Okay, and that will be accomplished if I pass this signal through a filter with a peak gain of 20 dB and rejection of minus 80 dB at f1 or omega 1 and omega 2. So if this is minus 80 dB, okay, so if I am passing the interferer level is going to become, minus 80, and signal level is going to become 0 dBm. So you will have 80 dB difference. Of course, that is intuitive from here itself. You can see that. So there will be 80 dB difference because signal is being increased by 20 dB and this is reduced by 20 dB, 860 dB. So the total difference will now be 80 dB. Okay, it will be more clear in the question paper, but here I just explained what I was looking for. Now for 80 dB, I said is if you split equally, you will have to give 40 dB of rejection in the band pass filter and 40 dB of rejection in the baseband filter. Okay, so I have not given FC in the question. Assume, if you can assume a certain FC of 1 gigahertz, then you can compute for 40 dB rejection what is the Q necessary. We just discussed the rejection is simply Q by, I think it is 2 omega naught. So 2 into 2 pi into 1 gigahertz. So this rejection is I should take 20 log of this, or I can use 40 dB is simply 100, 10 square, 40 dB. So 20 log of I mean 40 dB equals 20 log of this. So if I take, I'll get, I'll actually get this value, what I wrote here. Okay, from this I can get the value of Q necessary for this. Okay, from this equation itself you can actually see, there is, I think, rejection, there is also delta omega that I have to multiply. So I'll have to multiply this by delta omega here. Okay, so if F1 is given, so if I give you the frequency difference, F1 minus Fc will be your delta omega. Okay, so from that you can compute the value of Q from this equation. It will turn out to be a very large number. Now in the second problem, I have said if you can split equally between the three stages. I have said 80 if you split equally, I'll assume 27 dB per stage. So 27 dB, 27 dB and 27 dB. Now if you look at it, the Q requirements here comes down by 12 dB. So previously it was 40 dB, which is 100. Now 27 dB, so for example 20 dB corresponds to a gain of 10, rejection of 10. 27 dB, it's like 26 dB, I'll assume 12, 10 into 2. So 12, approximately the rejection is 12. Instead of 100, it becomes 12. This equation will become 12. So everything else remains the same, Q delta omega by 2 into 2 pi into 1 gigahertz. So from this equation, if you see, your Q comes down approximately by a factor of 10. That's a big change. So that's what I wanted to check in this question. Okay. In fact, if you want to do it more intelligently, you can split 20 dB here and maybe add 7 here, plus 7, it will be 34 dB here. Okay. So and if you see, your Q properly comes down by a factor of 10 itself, completely. It will come down by a factor of 10 for the first bandpass filter. So that's what I was testing in this problem. Okay. So now I've discussed this question here. So what is the Q required by the bandpass filter, IF and the BBF filters? When IF filter, your omega naught reduces by half, I think, in this case. So Q requirement will also further reduce because you will get more rejection. Because your omega naught reduces by half, you will get a factor of 2 improvement for every reduction of this IF frequency. So I could have chosen, for example, FC1. If I choose FC1 as 3 by 4 FC, then the intermediate frequency will be FC by 4. So I will gain by a factor of 4. Q can be lower by a factor of 4 than what it was for the bandpass filter, and still get the same rejection. Okay, and also it is much more realizable. If I go to FC by 4, it's easily realizable. Such filters with high Qs are really realizable. It's difficult when you want to realize it at higher center frequencies. Okay, so that's what this question mainly discusses about. I just wanted you to use this equation and compute the Q for a second. I didn't give more details because it was a tutorial. I thought, I'll discuss any unknown variables in the classroom itself. So I wanted to stress that this is more like a second order filter. Okay, I didn't tell you what is the order of the bandpass filter and all that, but generally it's a best is the simple second order bandpass filter. The simplest bandpass filter is the second order bandpass filter. Okay, for that this equation is valid. Okay, from this you have to compute the Q. For the first case it will be very large, in the second case it will be 10 times smaller. I just wanted you to see that in this problem. So taking linearity, the third part of the question is taking linearity into account. What can you comment on the linearity requirements of the LNA in both the receivers for the same rejection of the interferers? Now the main problem here is that if the bandpass filter in both the cases, in the second case, because your bandpass filter is little relaxed, okay, the LNA has to be more linear. If I give the same gain, this is the important point. If I'm going to give significant gain in the LNA, then it has to be more linear. But now that I have more stages to gain it up, I have to gain up my received signal. I'll gain it up in the mixer, in the IF filter. I have extra stage to increase the gain. So I'll give some amount of gain of the LNA to the IF filter. Okay, and then I can relax the IAP3 requirements for the LNA. So you can say that, I just wanted to comment on the linearity requirements, keeping that point in mind. Okay, now even the 0 IF receiver, if a bandpass filter is not able to provide this rejection, and you need to give most of the gain, you need to give a good chunk of the gain in the low noise amplifier, so then linearity takes a hit. Because if this is going to get a lot of gain, then the baseband filter and mixer will start getting hit. Because they have to be very, very linear. The stages following that has to be very linear. Okay, in this case I can have lower gains because and once I filter it in IF further, these two can have much relaxed linearity requirements. The baseband filter and the mixer, IF mixer, linearity requirements are significantly reduced. Okay, so this is the advantage we have from heterodyne to 0IF. Mainly we go for getting realizable Q. That's the important thing. It slightly relaxes the linearity requirements as well, but the more important point is the realizable Q of the bandpass filter, that we can make it practical in heterodyne receivers. But heterodyne receivers come with a host of its own problems. One of the main problem which I discussed in the class is the image frequency. So if you have, this is your local oscillator frequency, I said your RF frequency say is here, FRF is the RF frequency, then the image frequency will be here. I mean the intermediate frequency will be somewhere here. This will be FLO minus FRF. That will be your intermediate frequency. Okay. Now the way in which the down conversion happens, this will come to this frequency, or unfortunately if there is other frequency called the image frequency, that is if I move FIF from the FLO frequency, that is FLO plus FIF will be here I've actually assumed in this case your RF frequency is greater than FLO. This is called low side injection. Okay, this is called low side injection. There is other thing called high side injection, in which case your FLO will be more than FRF. Your FLO will be more than FRF. Okay, now this will also down convert. If you down convert this, you will be getting it to FIF. So if I move FIF from the FLO, the center, the carrier, the local oscillator frequency, even here this signal will also be down converted to the same FIF. Again, because when you take cosine functions, FLO minus FRF, and I take the mod of it. Okay, both of them will down convert to the same frequency. So this point is called the image frequency. Now the image frequency is a major issue in heterodyne receivers. So we need to introduce an additional block called the image reject filter. Okay, so we need a filter which can reject the images. So this is that filter is called image reject filter, IRF, or the image rejection ratio. There is a word called image rejection ratio. So after you pass it through the filter, you will see, or to the receiver, you will see how much the image gets rejected. So we will have to define IRR, image reject ratio, when you define heterodyne receivers, when you go for heterodyne receivers. So that's one of the main problems. It comes with other host of problems, but I just discussed only this main problem for heterodyne receivers. Okay, so that's it. So I've covered what you're expected to know, at least from the tutorials. So you can read up the textbook and then watch the videos that we already have posted so far. Okay, and yeah, I've also posted the instructions for the exam I've also mailed the instructions for the exam. So you'll have two parts, part A and part B. Part A, you'll have to return it back. So let me just write it. So part A, you'll have to return it back. It's for 40 marks. I've given plus 5 bonus points. It's mainly, the total maximum is 45, but it will be, it's mainly for 40 points. Then part B is for 30 points, because compre has to be for 70 marks. So that was the initial plan. 35 into 2 is 70. 35% of the course is compre, 70 marks. And but I have set the paper for 85 marks. So it's 85 is, more than that is bonus. If you score above 70, it's well and good. Okay, so plus 10. Part B is plus 10. So part B is like your regular comprehensive exam. You write it in the main answer book. I'll give everything in the beginning of the exam itself, both part A, part B, a supplementary book and a main answer book. Supplementary book, you'll be using it for part A. Okay, for part A. Again, I'll give you extra supplementary books for if you want to write it, if your part B answers, because there are only few questions in part B, but lengthy questions, 30 points. Okay, so if you want any extra sheets, I'll give you separately, but the supplementary sheet I give you initially is mainly for part A. You can do all your rough work there, and you'll have to return it, but I won't correct that. I'll only correct the answers that have been written on the main answer book, the main question paper itself. So I've provided blank spaces in the question paper. You have to write your answers in the blank spaces. Okay, so that's all for this. So all the best for your exams.